Hello. So please read the graph and answer about a question about the amplitude. So these numbers represent meters. So 0, 1, 2, and this axis represents time, 1 second, etc., etc. So you can look at the graph and choose your answer about the amplitude. What's the next slide? Okay. So I'm going to keep collecting your data. So again, the amplitude A equals 1, 2, 3, 4, 5, 6, 7, 8, 9, 0. So now we're going to do the motion equation. The motion equation, in general, requires some extra work. We know that in most situations, we're going to talk about only a cosine function or a sine function with no additional parameters. But in general, well, there are additional parameters like initial phase and that constant b. So what do we do about that? Well, you're answering the question about the amplitude, which is the maximum displacement from the equilibrium. And we also need the angular frequency. Angular frequency is related to period. We need to get the period. To get the period, we should choose two convenient points. Well, this is rather clear. So I'd say this is, okay, 2.53, 3.54, 4.5. And I say this is 2.53, like 3.1. And this, of course, is not the whole period. This represents a half of it. So if a half of a period equals 4.5 minus 3.1, 1.4 seconds, the period itself is about 2.8 seconds. And the amplitude is so it's about counting 0, 1, 2, 3, 4. So 2 amplitudes equal to 4 meters. Here we are assuming international system of units. So 1 amplitude is indeed equal to 2 meters. Now we can start writing the motion equation. That's what we know. The angular frequency equals 2 times number pi divided by the period, which is 2.8 seconds, times the time as a running variable, plus this parameter, which we call the initial phase, plus this parameter, which is another constant. So here we have 2 unknowns, basically, we have to solve for. Yes? So, if some more people miss this question, this is a second opportunity. If you've answered already, you don't have to do it second time, but if you're late a little bit, so you can press again. I don't believe 52 people were late. So, okay, it's up to you. If you want to press, if you want to answer second time, answer. Okay, no problem. So, to calculate, to find out two unknowns, how many equations do we need? Two. But we don't have those equations. So what do we have to do? We have to manufacture those equations. This equation, the motion equation, connects any instant of time with a specific location of this object. Any means any two. So we can choose two convenient times, and we can write this general equation specifically for those two instances, for those two locations of this object. And normally, as we know, if we have a zero, that helps. So we have two zeros here. 1 0 is when time equals 0. What? So we have two variables, running variables. Of course, time equals 0 at a certain point, and also we can see x equals 0. Well, actually many, many times, but at least once. So when time equals 0, we should read this number. So 2.53, 3.5, like 3.8, something like that. It's not exactly 4. From a general point of view, numbers don't matter. The strategy matters. Now, a second convenient point is here. So x equals 0 at that instant. And that instant is not 1. It's not 1.5. It's about 1.4, a little bit less than 1.5. So now, what can we do? We can use these given numbers, plug them into the general equation, and write two specific equations. For example, 3.8 has to be equal to 2 times cosine of 2 times pi divided by 2.8 times 0 plus theta naught plus b. That's one equation. And another, 0 equals 2 times cosine 2 times pi divided by 2.8 times 1.4 plus same constant plus same another constant. So now we have two equations and only two unknowns. Well, 3.8 divided by 2 is 1.6. Has to be equal to cosine of theta plus b. Here, 0 times anything is 0. 0 plus anything is that thing. So what's left is this. And here, what can we do? 0 equals 2 times cosine of theta. Bless you. Now, what's happening inside? 1.4, 2.8. So we can cancel 1.4, 2. 2 and 2 cancels, pi. I disagree. Well, now you have to look back in your memory, and there is a relationship which helps us to simplify this expression. Cosine of certain angle plus a fixed number pi. So there is, in trigonometry, there is a relationship. Cosine of is equal to, please tell me a suggestion. What can it be equal to? Exactly. So that helps us to simplify the second equation. And now, well, you have two equations to solve, and well, for example, we can subtract, right? Let's see if I'm so if we subtract these equations, b canceled. Subtraction gives us 1.6 minus 0 on the left-hand side of this equation, 3 cosine of theta, and that's it. So the cosine of theta will be equal to 1.6 divided by 3. That's all we need to know. So now we just have to take a calculator, use the inverse cosine function, and calculate the theta. That's the first step of a calculation. The inverse cosine, parenthesis, 1.6 divided by 3, close, equals about 57.8 degrees. So I rounded to 58 degrees. And what is wrong with this number? It's in degrees. Because we have to use international system of units. Time has to be used in seconds. Pi means 3.14. It doesn't mean 180. This number pi means 3.14 radians. So when we finish our calculation for the phase, we should use radians. 58 degrees is very close. It's about 1 radian. So when I'm close to the edge, I can't write at all. So the software is very accurate, 1 radian. And now, what can we do? Well, we can plug that number back into first equation, for example, and calculate that number b. That's it. You can do it on your own. This is 1 radian, or 58 degrees. So 1.6 minus cosine of 1 radian equals b. Done. So this is how, in general, if you need to, you can always calculate those two additional parameters. Any questions? So let's see, what do we have now? Still 2. Okay. A good sign. All right. An object is released from rest, a very common situation. That's what we usually talk about. And it starts from rest and et cetera, et cetera. Write the motion equation. Well, first of all, we have to make a choice between, well, again, in general, we always have 3 choices. We should choose pure cosine, or pure sine, or see, no other parameters are involved. Or something like we just had in general. This covers all possible situations in the universe. But these two related to the way the motion has been generated. Yeah. So in this situation, what do you choose? Missing people. And of course, depending on the choice, the graphical representation also should look differently. For this choice, the graph should look like this or like this, and etc., etc. For this choice, the graph should look like this or like this. And for this choice, a graph can look any way. Well, actually, it's practically cosine. I don't want this. So something like this. Smoother, yeah, smoother. This situation, number 3, just has been solved 2 minutes ago. But we don't have to do it every time. If the description tells us what kind of a case is happening, number 1 and number 2. So I'm going to stop collecting data in 15 seconds. If you didn't press your answer yet, do it right now. And the next step, of course, is, well, if we have chosen the equation we want to use, we start writing the motion equation. The motion equation looks like this: x equals x equals the amplitude times that function, and then so this is what is happening. Not the motion yet, not the motion yet, not yet, not yet, not yet. Go. So your choice should be based on 2 things. Number 1, is initial velocity equal to 0? Yes or no? And does it start from the equilibrium? Yes or no? And after that, if you tell to yourself the initial velocity is, and you should write it down, that's your answer. In this particular problem, the initial velocity, V initial, is, and you should write something. So in this situation, in this problem, the initial velocity equals, well, either 0 or not 0, you should choose. The initial position is equal to either 0, where the equilibrium is set, or not, you should choose. And after this, you should answer the same question one more time. Please. Again, now I have to time it. Where is it? Here. Some of these graphs represent a situation when initial velocity is 0, but initial position is not, and actually is equal to the maximum displacement from the equilibrium. And another graph represents a case when initial position is 0, but initial velocity is not. You can use this time to take a short nap. Relax. Okay. Now, as we can see, the distribution changed significantly. So the way you reasoned through this question now should become a part of your thinking strategy. And the answer now, of course, is number 1. The correct answer is the number 1. So I'm just going to... I'm just going to write it again. X equals amplitude cosine of angular frequency times time. That's it. Everything else is irrelevant. Now, we need 2 numbers to finish this equation. The first number represents maximum displacement from the equilibrium. And of course, that's supposed to be 10 centimeters, which is equal to 0.1 of a meter. If we release it from rest, the initial speed is 0. That automatically means the initial position equals the amplitude. It can't go any farther away from the equilibrium than that point. That's done. Now, this one. Well, there is an equation we can use. It has to equal to a square root of what? K over m. So 10 over 0.1. Because again, we can't use grams. 10 over 0.1 is 100. Square root of 100 is 10. 10 what? Radians per second. If we're using international system of units, everything automatically has, well, the correct unit. So now we can finish our equation. It's going to be equal to well, plus or minus. This word also is important because our positive x direction is to the right. So if we started moving like this, if initially it moves in the positive x direction, so the initial position is positive. But if our positive x direction is to the right, but we released it in such a way so it initially moves to the left, that's 0. So where is my positive x direction? We don't need, so this is the motion. Well, initial velocity is 0, but in a fraction of a second, the velocity points like this. So yeah, we should choose a plus. Plus, the graph for the position as a function of time should look like this. Velocity represents the slope. The slope is supposed to be negative. Everything is consistent. The amplitude is equal to 0.1 cosine 10 times t. And immediately we can add 2 more equations. The velocity. Well, first of all, in general, Well, we just have to visualize the slide with those three equations. The first equation is on the screen. The second equation, it's this. So we just have to write everything down. 0.1 because it's amplitude, 10 because it's angular frequency, sine 10 times time. Now, normally we don't show these parentheses. We mean them. We usually indicate parentheses when there is plus something inside it. But we have to remember that both factors at 10 and time represent the product, which is inside kind of that function we call cosine. Because sometimes people make a mistake by calculating cosine of 10 times a t. That's not what it is. And finally, for the acceleration, what else can we write down? Well, force. We know that the force is related to, well, again, we only considering one situation when the origin is at the equilibrium. So in that case, no delta is just x. All right, so the x component of the force is equal to this. That's a Hooke's law. So negative, what is a k? 10, that's a k, times, well, x equals 0.1 cosine. So only first equation has a specific name. We call it the motion equation. Well, but we could call this velocity equation, acceleration equation, force equation. What else? Well, energy. Kinetic energy. mv squared over 2 was as one of the options. But in this situation, the easiest one, because we know everything, mass equals 0.1, and velocity, well, equals this. So 0.1 times 10 is 1. If we square it, negative doesn't matter. Negative 1 squared is 1. So that's going to be sine squared of this. Potential energy. Well, it could have been total minus kinetic, or it is equal to kx squared divided by 2. So k equals 10 x squared. Well, now the whole thing has to be squared. 0.1 cosine 10 times time squared divided by 2. Now, work. This is divided by 2, and this is 10 times. So it looked like 10 squared. I don't want to confuse you more than I already have. So, and if you add them up all together, that will give you total energy, kinetic plus potential equals total, just mechanical energy, that's what we call it. And it actually has to be a fixed number. If there is no friction, it has to be a constant, a certain number. So we don't have to add these two expressions together. We don't have to do that. We know that when the cart is reaching the maximum displacement, the kinetic energy has to be 0. So at this instant, total energy is equal to potential reaching maximum. So to calculate this constant, the easiest way is using the expression for potential energy, K times, if it at the maximum displacement, x becomes equal to the amplitude divided by 2. So k is 10. The amplitude is, let's write it down, 0.1. 0.1 squared divided by 2 by 2. So I've answered many slides ahead, but why not now? Exactly same example, but now we don't have a graph given to us. Instead, we have an equation. So I'm not going to repeat all the reasoning. I just want to extract the immediate information from this equation. Well, first of all, now this is not a cosine, this is a sine. So, well, the acceleration will be this. The force will be equal to this, the x component of this, not the magnitude. The kinetic energy, well, potential energy, that's easier, is equal to this. Kinetic energy, oh, okay. Total energy is equal to this. And kinetic energy is equal to either this, total minus potential, or this, mv squared over 2. So that's all clear. Omega is equal to k over m. So that equals to 31.4 radians per second, because that's what we read right here. The number which is between the, well, n and t, that's the angular frequency, 31.4. And if we square it, k divided by 2 kilograms should be equal to 31.4 squared. So to calculate the constant, we just need to calculate this. That's the constant, spring constant. And this number 5, of course, is the amplitude. That's the maximum displacement, the maximum value of this x. By the way, I didn't mention, but you see this variable, capital A, has a name, the amplitude. But the same word might have a different meaning. This whole product, that's the maximum speed of this cart. But the word maximum is a synonym to the word amplitude. So people also could say, this is the amplitude of the speed, or amplitude of the velocity. This is the amplitude of the acceleration. This is the amplitude of the force. So this word amplitude might mean maximum, but normally it just means maximum displacement, amplitude of x. So here, we should assume meters, a Newton over a meter. And what's missing? Velocity. Well, we know the equation for the velocity when position is a cosine. So now we got to write an equation for the velocity when the position equation is a sine. Well, of course, it has to be plus or minus. We have to choose. Of course, it has to be amplitude times angular frequency. And of course, it has to be another function. You see, if you look at these expressions, the function changes. If we start from cosine, the next function for the velocity, for the slope, is a sine. If you know calculus, you just have to calculate the derivative. That's it. But we don't know calculus. That's why we have to spend so much time on this topic. And the next, so the acceleration represents the slope of velocity. So we change it again. So the same thing is happening here. If position equation is given as a sine, the slope of the sine should be a cosine. So we should write the cosine. They must have exactly the same angular frequencies, same number, times time. So we know A, that's 5. We know omega, that's 31.4. So V max, maximum speed, is equal to 5 times 31.4 meters per second. The only thing now left to choose is plus or minus. Well, it's about the slope. So this is the graph for the position as a function of time. It begins from the x and it goes upward. So the slope at x equals 0 is positive. That's it. So we have to erase a minus and keep a plus. That's the velocity equation. Now we have all the equations. This is the equation for the acceleration, for the force, all energies, done. Question? Calculate. Well, if we have all the equations, we now just have to plug in numbers, right? So here, we don't relate velocity, acceleration, or force, or energy with time. We should relate it with the position. So there are two options to do that. We can try to do it directly, so we can derive an equation which relates velocity and position, or we can use a time as a middle variable. For each given position, of course, there is a time when that position is reached. We can calculate that time, and after that, we can use all the equations we had to calculate anything we want to. So that's the fastest approach in most situations. So let's do this. If x equals 5 centimeters, okay, let's convert it into meters. But the cart was released from rest. This word rest immediately tells us what function should we use. It has to be a cosine attached to a spring, moved centimeters away. This is an ambiguity. We know it's away, but we don't know in which direction, to the right or to the left. So in this situation, we should ask that additional question, because depending on that question, we should choose a plus or a minus. Let's assume that it was moved to the right, so it's moving initially to the left, so we should write plus 0.1 cosine. What was the angular frequency equal to 10? Same numbers. Yeah. Angular frequency still equals k over m, so times time. This is the motion equation. For any x, we can solve it. So in general, x divided by 0.1 should be equal to cosine of this. Now, if we take the inversed cosine of this, that gives one of possible answers for the time. The same position is reached periodically many times. So this is when it reached the first time. Yeah, for the graph, like this, we start from 10 centimeters, well, 0.1 of a meter, okay. And we go down, and et cetera, et cetera. This is 5 centimeters, 0.05. So this position, first time, is reached at t equals 1. second time is reached at t equals 2, third time is reached at t equals 3, and no friction, it moves forever, so we have infinitely many instances. Yes? 10? What do you mean by 10?
It's cosine of 10 times.
It's not, no, it's here yet. Thank you. And now finally, yeah, to calculate time, the inverse cosine of this divided by 10. So if x equals a half, if x equals 5 centimeters or 0.05 of a meter, the first instant for this time, inverse cosine of 0.05 divided by 0.1 divided by 10, so the inverse cosine of 1/2, yes? Yes, divided by 10. In many situations, we don't need to know the exact value of x. All we need to know is the ratio between the x and the amplitude. That's what is calculated right here. This is a half of the amplitude. It could have been a quarter of the amplitude, 1/3 of the amplitude. So as long as we know this ratio, x over a, yeah, we're done. Cosine of 60 is equal to, so 1/2, so that should be 60 degrees divided by 10. Don't work because we can't use degrees. So 60 degrees, pi over 3 radians, pi over 3, pi over 30. That is the first instant when this position is reached by this cord. And we can calculate now all other instances, all other times. In general, of course, if we solve this equation, the solution is t is equal to 1 over omega, the inverse cosine of x over a. That answers all possible situations, all of them. Moving on. And of course, if you know this instant, now you can use this answer pi over 30, and you can plug it in all these equations and calculate anything you want to. Energy. Okay, I don't have time to ask this question. So here, red lines, as we know, represent the potential energy as a function of the position. Blue lines, blue curves represent kinetic energy. What's the difference? Well, something is different. If you look closely, this graph is related to angular frequency, which is equal to 1 radian per second. This angular frequency 0.8. So we have two different systems. Angular frequency is different. It means either spring constant or mass, or both are different. So, and can we figure out what? Well, yes, we can. If we read these graphs, so for example, here, x equals 1, and that's the amplitude. It doesn't go any further. And the energy here, which is the total energy, which is equals to maximum value of potential energy, which is also equal to maximum value of kinetic energy, is equal to 500 joules. So we can use this fact to calculate this constant number 1. And if we use the same reasoning here, the maximum energy is equal to like 320 joules, and it has to be equal to constant times, well, same amplitude, squared divided by 2. So that's why graphs are different. We have two different cards. We moved away each card by the same distance, well, 1 meter. So the amplitude is the same for both. But turns out the spring constant is different. Can we say something about the masses? Well, 1 is equal to square root of spring constant over mass number 1. And 0.8 is equal to spring constant number 2 divided by mass number 2. We also can figure out masses. And we've seen this slide before. If we want to, we can also, we haven't seen it yet, but we can also plot the graphs for the energy as a function of time. Basically, for example, the potential energy as a function of time. Potential energy, time. We know it has to be equal to k x squared divided by 2. And this, well, the motion equation depends on how we made it move. So if we released it from rest, we should use a cosine. Cosine squared omega t over 2. So this is how a cosine looks like. And if we square it, what's happening? All negative parts become positive parts. So the graph now going to look like this, etc., etc. So if you look at this graph for the position, that's going to be a period. It repeats itself in a certain amount of time. But if you look at this graph, this is actually this. So the period of energy, well, potential energy, is equal to a half of the period of the position of velocity. Same true for kinetic energy. For the kinetic energy, the fastest way is calculating, well, you know, kinetic energy equals total energy minus potential. But total energy is equal to maximum value of potential energy. So the graph is going to look like this. Again, this is for the case when the card has been released from rest. That's why initially it has no kinetic energy. Then kinetic energy reaching maximum, 0, maximum, 0, etc., etc. But if instead of doing this, oops, we would do this. Now, potential energy starts from 0. So if we want to choose which graph should represent potential energy, we should choose the blue one because it starts from 0. But kinetic energy, well, starts from the maximum value, goes to 0, etc., etc. Okay. I want to ask you this question, the last one. For this one, I have time. We had a very similar question for an object falling down or tossed up. And now, let's give you a minute. What can you say about the total energy of this total energy, total which is potential plus kinetic, right? Thank you. So everybody who has pressed something is free to go. I'm going to still wait for 12 more seconds. If you want to see it. The right answer is 3. It's always positive. Kinetic energy mv squared, potential kx squared, everything is squared, everything is positive. It's always positive. So we have one more lecture left on this topic. I'm going to go over the more examples, more situations. Anybody who is seeing attendance sheet, please wave. People looking for attendance sheet. Over there. I think. No? No? Please don't steal the attendance sheet. I need it. Where is it?
They failed over there.
Where is the attendance? Yes, yes. No. I think it's over there. I see a person with a piece of paper in hand. Yes, you should. Just please take that piece of paper. What's today? 6th? No, 8th. Yes. So please just write April 8th. Yes.
Yes, I just want to make sure you posted the equation sheet for exam 3 on so that
No, I haven't posted it yet, but I'm going to do it probably over the weekend.
okay, cool. Thanks.
No. Well, yes. So you can, yeah, you can write your name. That's it. Thank you. What happened? Shoot. Two 52, 254. Okay. You can shut it down and just unplug everything. I still need a minute here. Yes.
What calculation did you do here? You took, so you had this, and then you made like some conversion to negative cos of alpha. I didn't catch what this was.
No, this has nothing directly to do to this. This is a law, not from physics, from math. This law says that cosine of any angle plus pi radians will give you the same example, the same number on a calculator as -1 times cosine of the same angle. So if you take a calculator and if you calculate cosine, let's say 1.2 radians plus pi, and if you calculate negative cosine of 1.2 radians, it will be the same. That's a law. It has been proved in trigonometry, and it works for any angle. But this law now I used here. I used it here. I said because of this law, cosine of pi plus theta has to be equal to -1 times cosine of theta.
Okay. Okay. Thank you.
I'll take care of the rest. Thank you.